In recent years, increased appropriations to hypersonics has made the rapid development and fielding of hypersonic weapon systems crucial to winning government contracts. During flight, hypersonic vehicles experience rapid thermal loading, making the choice of material crucial. However, currently published temperature yield curves in material datasheets are based on a long-duration furnace method that does not account for the instantaneous effects of heat on yield strength. The goal of our project is to develop a proof-of-concept lightweight apparatus which is capable of heating a dog bone structure to 2,000 degrees in 10 seconds and then performing a tensile test.
Meet our team. From left to right, we have Sam, a mechanical engineer, Chris, a material science engineer, Brandon, an electrical engineer and our procurement lead, Esther, an aerospace engineer and the team lead, Chase, a mechanical engineer, and William, a software engineer. Additionally, we are assisted by our mentor, Mitch Mosfett, and the help of our sponsors, Cameron Crowley and Connor Raskin at Northrop Grumman.
Our project was centered around creating a rapid heating tensile tester that could better mimic the kind of thermal loading materials experienced in hypersonic flight. So some of the objectives were to heat a sample very quickly so we could study how it responds under extreme temperature changes over a short time. At the same time, we wanted the system to stay low cost, lightweight, and practical, with a design that could be carried by 2 people and set up without too much difficulty. Another major objective was collecting live data during the testing, including load, temperature, displacement, stress, and strain, so we could fully capture the material response. We also focused on designing a structure that could safely support the forces involved while still being straightforward to manufacture and assemble. Efficiency was another big part of the project, since producing tests quickly meant we could gather more data across multiple samples. And throughout the entire design, safety was a number 1 priority, so features were included to help limit the risk during both heating and operation.
During the early days of our project, we wanted to ensure that the frame-up for our apparatus could withstand the loads it was going to be subjected to. We did this through the use of first-order hand calculations for bending stress in the aluminum base and crosshead, as well as buckling for the steel columns, bearing stress for our pins that connect the grips to both the linear actuator and load cell, and a thread analysis to make sure that the bolts and threaded inserts could withstand the forces that would be applied to them.
To get an estimate of how much power was required to heat the samples, we first did a theoretical approximation just using the conductive thermal energy required, and then did a power estimate using 10 seconds. The next thing we did was introduce a power efficiency of 5% to estimate the torch's efficiency factor. This gives us a better estimate of how much power was required to deliver to the specimen.
When researching initial ideas for how we wanted to build the tensile testing part of our apparatus, we considered multiple sources, as well as input from our project mentor, Mitch Moffitt. We also looked at designs where the tensile tester lies horizontally, as well as ones that stand upright like you would see at a typical Instron machine.
Our graphical user interface is implemented as a Python-based scripted desktop application. It communicates via serial connection with our Arduino microcontroller, which implements the device's firmware. Our Arduino receives input from 3 sources: load input from our load cell amplifier, temperature from our max thermocouple amp, as well as feedback from our linear actuator, which is processed using a low-pass RC filter to reduce noise. It then sends control signals to our Cytron motor driver, which receives power from our power supply and then modulates that to allow us to control our linear actuator.
Our project, we conducted a total of 4 different case studies. The first one was for the dog bone. Here we concluded that the 330 stainless steel with a 0.12 inch diameter was the best option. Number 2 was looking into the heating system. Here we compared the inductor, heater, resistor heater, combustor heater, and infrared radiation, which we ultimately decided to go with the inductor. However, due to some failures, we are now going with the combustor heater. The third case study is on the heating measurement, which we compared a thermocouple, parameter, along with the thermal imaging, and we decided to go with the thermocouple. Last but not least, we compared microcontrollers, which included an Arduino Mega 2560, an FPGA board, and a Raspberry Pi, and we ultimately decided to go with the Arduino Mega 2560.
Though all of our system requirements were important, only 5 of them drove our actual design. 2 of them were most important because these were the ones that mimicked hypersonic flight. The first of these is that the heating system shall heat a dog bone sample to 2,000 degrees Fahrenheit in 10 seconds, and the second is that the linear actuator shall be able to apply 1,000 pounds of load. Our other 3 system requirements were based on how the apparatus is actually going to be used. The first is that it could not weigh any more than 200 pounds and should operate on 120 volts from a standard wall outlet. Lastly, the user interface shall apply live data for the load, stress and strain, actuator displacement, and current temperature.
This segment shows how the original point design directly drove the final system. Early on, the main design elements were the heating system, the temperature measurement device, and the controller, because those were the components most closely tied to the major project goals. From the beginning, we needed a system that stayed under 200 pounds, operated from 120 volts, heated the sample to 2000 degrees in 10 seconds, and applied over 1,000 pounds of tensile load while displaying live test data. In the final design, some of those elements stayed the same and some evolved. The heating method changed from an inductive heater to a propane torch, but its role remained rapid heating of the gauge section. The thermocouple stayed in the design for temperature measurement, and the Arduino Mega was still used as the controller for the linear actuator and thermocouple input. Mechanically, we changed from a motor and crosshead style concept to a linear actuator, which reduced unnecessary movement and simplified the system. Overall, the point design gave us the foundation, and the final design refined it into a more practical and achievable system.
All of our system requirements have passed, with the exception of 3 that are still waiting final verification. Our first group of system requirements on portability all passed, with the apparatus being within its size and weight limits. We accomplished our safety system requirement by having an emergency shut-off button and having shielding for the heating elements. Our measurement passed because our data uploaded at 10 Hz. The 3 that are still awaiting final verification are our repeatability and performance system requirements. First of all, we are waiting to confirm that this can be replicated 3 times in a row. Also, we are waiting to confirm that our heating rate does reach the 2000 degrees Fahrenheit in 10 seconds, and we are still waiting data on whether it takes less than 12 minutes per sample to test. A standard wall outlet is verified for our electrical system requirement, and for our mechanical system requirements, our actuator is software restricted, our actuator speed is more than 0.1 inches per second, our load cell has a capacity of over 1,300 pounds, and our actuator has a capacity of over 1,000 pounds. As for our user interface system requirements, our data is displayed live, is able to be saved to an output file, and allows the user to set a delay.
As you can see here, our apparatus was able to break a sample after heating it up to 2000 degrees Fahrenheit.
For customer deliverables, we have a total of 3 products, all of which will be turned into Northrop Grumman at the end. But the first one is a user manual, which will show people how to use the apparatus, and this will be delivered as a PDF. The second one is the prototype, which will be turned in as an apparatus. And the third one being a final report, which will be turned in as a PDF, and this will summarize everything.
Lessons that we learned as a team, firstly, was to begin manufacturing as soon as possible within the project timeline. Secondly, was to develop designs that are used in the project simultaneously instead of in series.
Since we were working with high temperatures and voltages during our project, safety was a #1 priority. This includes having properly soldered electrical connections and 3D printed housing for all of our electrical components.
For acknowledgements and references, I would like to bring up our sponsors, Cameron Crowley and Connor Raskin, along with our mentor, Mitch Moffitt, and our team, 26046.